Welcome back. Today is session 7. We're going to talk about climbs. Now, an airplane takes off, that's one piece of the pie. But after you get moving, then you're going to have to be able to climb up and get away and do your thing. If you can't climb, you're more like a hovercraft or even a helicopter that's just heavily loaded and can't go anywhere. So today's session, number 7, is all about climbs. Let's take a walk down the ramp, me and my P-38 Lightning model here, and we're going to demonstrate some stuff on the way. Now, the climb capability of an airplane is affected by a couple of different things. One of which is how high you are or how low you are, or how fast or how slow, and how heavy or light. All three of those factors are pretty important in determining just how fast an airplane can climb and how steep it can climb out. To understand the discussion of climb performance, we're going to have to define a few terms a little bit. Here's my P-38 Lightning in a climb, and that path that it leaves is called the flight path. Now, if we take a look at that flight path, you can break that into two components, the horizontal component and the vertical component. Now, that vertical component is the climb rate, and we abbreviate that as RC, rate of climb. Now, the angle between the flight path and the horizontal, that angle there is the flight path angle or climb angle, and we call that gamma, the Greek letter. Let's show how these are related to each other. You can sketch out the side view of an airplane as it climbs. The pilot reads the airspeed indicator in the cockpit. This tells him the speed along the flight path, v. Again, the angle of climb is that Greek letter gamma. From trigonometry, the sine of gamma is equal to the rate of climb divided by the velocity. This simple diagram equation shows that if we know any two of the values, then we can calculate the third. Let's apply this in an example. Suppose our aircraft is flying at 200 knots, or 338 feet a second. If the airplane climb angle is 10 degrees, then what is the climb rate? Plugging that into the equation shows that 338 times the sine of 10 degrees is equal to 58.7 feet per second for climb rate. Now that we have a feel for the geometry of a climb, let's go ahead and take a look at some of the factors that affect climb performance. Now, the math can get kind of complicated, so what we're going to do is make a simplifying assumption. The first simplifying assumption is that the angle of attack is small. Essentially what we're saying is when the airplane is climbing, it pretty much climbs in the direction that it's pointed, and it doesn't climb like this. The angle of attack between the wind and the airplane is small. Shown here is an aircraft in a climbing condition. Looking along the direction of the flight path, we can sum up the forces. Along one direction is the thrust force, and opposite to that is the drag force, and there's also some weight force. Let's take a closer look at this one. If the flight path is horizontal, then all the weight is perpendicular to the flight path, and there is no weight in the drag direction. On the other hand, if the plane is going straight up, then all of the weight acts along the drag direction. At some intermediate climb angle, the component of weight along the drag direction is the weight times the sine of the angle gamma. This is where Newton's second law comes into play. Good old sum of the forces equal the rate of change of momentum. Now that works whether it's a DC-3 or it's some new rocket. Same basic principles still apply. Unlike a rocket, the fuel burn rate of a DC-3 in a climb out is not much at all. It's only about 100 gallons an hour. So basically, it's negligible. We can get away with assuming that the mass of the airplane during a climb is constant, and we won't really ruin any of the accuracy. This simplifies the equation to thrust minus drag minus weight sine gamma is equal to the mass times the change in velocity over the change in time. If we wanted to, we could use this equation to show how the airplane can climb or accelerate at the same time, but then it gets kind of complicated. So let's just make a third simplifying assumption that during the climb, the airplane is flying along at a constant airspeed. That means dV dt equals 0, and that really simplifies the equation. Now, thrust minus drag minus the weight sine gamma equals 0. Or we can just rearrange that and say the thrust minus the drag is equal to the weight times the sine of gamma. We can use this rate of climb equation to do all kinds of cool things. Suppose I just got my brand new shiny, well, semi-shiny, captured Russian MiG-21 airplane, and I want to find out what the best climb performance is so I know what to tell my fighter pilots on how to fly the airplane. Well, to predict what the climb performance is going to be without actually flying it, what I can do is use that equation, and I only need three things: the weight, the thrust, and the drag. Now the weight's easy. I got my captured airplane, I put it on some scales, I can weigh it, that's done. Now let's talk about the drag. There's a bunch of different ways of figuring out what the drag is on an airplane, one of which I showed in session 4 where I took the glider and dove it down and timed this thing right with the stopwatch and all that. And there's some other methods too. Now to measure the thrust on the airplane, there's again a couple of ways. One is to tie the airplane down and run the engine and measure how much force it's trying to pull away and so forth, and we can plot up all that data. Or we can go to the engine manufacturer and get their predictive data on what the thrust might look like. Now, one of those thrust curves looks something like this. This is a sample figure for maximum thrust for an engine. You can see that at any one altitude, the thrust changes just a little as the airspeed increases. You can also see that for any given airspeed, the thrust gets smaller as altitude increases. For this example, let's pick a flight condition of, say, 300 feet per second and 10,000 feet of altitude. Here you can see the thrust is this value, 800 pounds. Now from a glide down test of this airplane, I found that the drag is 527 pounds, and at that time the weight was 7,800 pounds. Now if we plug that into the climb angle criterion, what we can see is that the total climb angle of the airplane is the thrust, 800, minus the drag, 527, divided by the weight, 7,800 pounds. And all of that is equal to the sine of the climb angle of the airplane. Now if we solve for gamma, what we find is that the climb angle of the airplane is 2 degrees. Not exactly the Saturn clock. Now I can also use my equations to figure out what the rate of climb is going to be at the same conditions. Remember that the rate of climb is just the velocity times the sine of the climb angle. Well, a velocity of 300 feet a second times the sine of 2 degrees gives me a climb rate of 10.5 feet per second. Let's go back to my board here and review the rate of climb equation. There it is. Let's do this for a given weight. Let's say 8,000 pounds is the weight of the airplane, and we'll see how the rate of climb changes as I change the velocity of it. Now, remember from session 4, we talked about the drag on an airplane, how it goes up with the square of velocity. So the drag force goes up with the square. And at the same plot, I also want to show what happens with thrust. So for this particular airplane, let's say the thrust decreases a little bit and then starts to increase as we go faster. The distance between the thrust and the drag, this vertical distance here, is called the excess thrust, because it's the thrust we have above what is needed just to overcome the drag. Now if we go to this equation, we can see that the rate of climb is the excess thrust times the velocity. So all I do is pick the velocity that I was looking at earlier and plug that velocity and that distance into this equation. Multiply it all out, divide by my 8,000 pound weight, and I get a rate of climb. Now I can plot that on this curve over here at that same velocity, get that product from the rate of climb calculation, and there's a data point right there. Now I can do this series of examples for a whole bunch of different airspeeds, and a curve ends up looking something like that. Well, let me show you why. If instead of testing at exactly that airspeed, I went a little bit faster, now you can see at the faster speed, the excess thrust is actually a little bit smaller. Going back to this equation here, this is a smaller number, less excess thrust, but the speed is faster. So the product of the two actually turns out to be a little bit higher. So to plot that one up, that slightly higher speed, I have a larger rate of climb. If we go a whole lot faster, say at this speed, now look at the excess thrust. You can see it's getting very small now. So even though the velocity is large in this equation, this excess thrust is so small that the total product is small again. And so at that velocity, if I was to plot the rate of climb, it would look something like this. So I just connect all the dots to get a curve like that. And that's basically how the rate of climb changes with airspeed. It's pretty much the same for jets and props. There's a few little differences, but that gets the basic idea across. An aircraft designer would use models to help predict what the drag of an airplane would be, to help figure out how much thrust it would need and what sort of climb performance it would get as it climbed up. Now my job is as a flight tester. I actually test the real thing to see what it's going to do. So instead of taking a little model like this one, we go out and we test the big one. Now this is the famous P-38 from World War II, made by Lockheed. And it's part of the museum that belongs to the Santa Monica Museum of Flying in Santa Monica, California. And it's in modification right now. But back in the days when this thing first flew, they had to do the same sort of testing that we typically do today. They took it up with their stopwatches and they timed the climbs. They timed several other factors. They looked at the airspeed. They looked at the weight of the airplane, how much fuel was on it, and put all of that into the equations, and they would reverse the rate of climb equation to find out the excess thrust. When they did that, then they can go back and figure out how well the original designers did in predicting the performance. We do that same sort of thing today, just like we did 50 years ago with modern airplanes, whether they're jet transports or fighters or anything else. The rate of climb equation also works for an airplane that is descending at a constant airspeed. All the pilot has to do is decrease the thrust until it's less than the drag. This means that the excess thrust is a negative value. If we plug a negative value into the climb rate equation, then the answer is also going to be negative. That means the aircraft is descending. If the excess thrust is a large negative value, then the airplane will descend faster. I showed this with the glider in session 4. Remember how the descent rate dramatically increased when I extended the speed brakes? That was because the brakes added more drag, thereby making a more negative excess thrust. Was that a lot of information or what? Let's review what we talked about today. First of all, assuming a small angle of attack, I showed that the rate of climb is equal to the velocity times the sine of the climb angle, gamma. Then, starting from Newton's second law, and assuming we had a constant mass and velocity, then I showed that the thrust minus the drag divided by the weight is equal to the sine of gamma. And finally, combining these two equations gives us the rate of climb equation, which is the rate of climb is equal to the velocity times the excess thrust divided by the weight. All of these equations work for any amount of thrust, drag, weight, or velocity, as long as we don't violate the initial assumptions of small angle of attack, small weight change, and no velocity change. Well, I don't know about you, but my brain hurts a little bit right now. I think I'm going to take a nap, dream about airplanes. See you later.